So hopefully last week you talked a bit about adjacency matrices and how you can use those to understand walks in graphs, and maybe also adjacency tables. There's certainly a couple of questions on the sheet about that, in which you just, instead of giving a graph pictorially, you give it by saying what vertices are adjacent to other vertices. So we'll see an example of that today. So what I want to talk about first today are essentially two separate methods. I'll write this down later, but two separate methods of searching through graphs, and at least one of which we've seen before when we discussed the colouring of vertices. We essentially used this method of writing down all the adjacent, one vertex at a time, and putting down all the adjacent vertices. That's called the breadth-first search method. And it functions with a queue. The data is held in what's called a queue, in which you shove vertices, say, on the right, and you take them all from the left. So like a bus queue. But we're going to start today with another form of searching, which has different characteristics, because it tends, rather than sort of searching all adjacent vertices from the start, it tends to go deeper and get more quickly further deep down the graph, or the tree if it's a tree. And the idea with these searches, you typically apply it to, you can imagine it being applied to a maze, for example. You can, as a problem to sort of understand, you can suppose you're trying to get from the start point here of a maze to the finish point. So what you do is you take a maze like this, in which the black edges are walls or hedges, and you convert it into a graph in which the red edges here are just the paths you can go along the corridors, some being dead end, of course, dead ends. In fact, this sort of graph, it's easy to sort of produce one by hand, because you can just imagine that, apart from the outside part, the edges on the inside, you can either have them, or you can think of starting with a grid in which all the edges are present, and then you sort of turn some of them off. So you open up doorways. So you can even do this probabilistically. So there's some quite interesting mathematical problems concerning probability. If you suppose that you have an edge with probability a half, you can then ask what's the chances of getting a path that goes all the way through the maze, that sort of question. But anyway, in this situation, we're not talking probability. We have a definite graph which we want to essentially investigate from some starting vertex, and perhaps we're interested in getting from the start 7 to vertex 10, which is the finish. And just to remind you, you can solve this by computer if you're interested with relevant programs. And the way you'd insert this graph into the computer, if you used, say, Sage, you might do it by just giving this adjacency data. So this is just basically an adjacency table, in which we're just saying if you take the vertex 1, it's adjacent to edges. Vertex 1 is adjacent to edges 4 and 6. Vertex 2 is a dead end. It's only adjacent to 3, and so on. Okay, and then I'm going to explain this in a more abbreviated form, but the idea of a depth-first search is you use not a queue, but something called a stack. So remember, think of the stack of cafeteria trays, in which you put, each tray is a vertex, but you put them on the stack, so you can only actually take off from the top. You're not allowed to take off from the bottom, and that makes a huge difference in terms of what's actually achieved. And the notion of a stack is very important in informatics. It was actually introduced by Alan Turing, probably in the 1930s. I think he was the first person to imagine that a computer could use the idea of a stack. So in this case, why is there 7 at the top? Because we're going to start with vertex number 7. I'll do this by hand in a moment. And then we start with 7, and 7 is adjacent to 2 vertices. It's adjacent to vertex number 3, and it's adjacent to vertex number 12. Now, if we were doing a breadth first search, we put both of those vertices in the queue. But for depth first search, I'm only going to put the one vertex, one adjacent vertex on the stack, because I don't want too many things on the stack, otherwise I can't sort of get rid of them. So I use numerical order, so I'll only put 3 on the stack. So after 7, we'll put 3, and then 3 is the top of the stack, so we can use 3 to look at other adjacent vertices. Now, the smallest vertex adjacent to 3 is 2, so that goes on the stack. That's then useless because we can't go anywhere from 2, so 2 comes off the stack. That's called backtracking. We go to 2, but we have to backtrack to 3. So tray number 2 is taken off and thrown away, and then we're back at tray number 3, and from there we can go to tray number 9. That's the idea, and here's the sort of way it's written down in detail. We started with vertex 7. This is written, the stack is written horizontally, so the bottom of the stack is the left-hand side. So 7 never gets removed until right at the end of the game. So 7 is at the bottom of the stack. 3 goes on top of 7, 2 goes on top of 3, that gets removed, you're back to 3, and then 9 goes on, and so on. And you can get to 10 if you want. If you think of 10 as the finish vertex, you can stop. Otherwise, you can get most of the vertices, but you'll never get with this method the vertices 11, 12, and 8, which were in this little clump here. So in the depth first search, the way I've implemented it, you don't see those to start with because you only choose one vertex at a time. So you do all this part of the graph, and then you realise you haven't got all the vertices, so you have to backtrack all the way down to 7 to capture 12, 8, and 11. So in the history of the stacks, they come at the end. But by the time you've finished, you've then gone through every single vertex, you've added it to the stack, and you've removed it from the stack. And that's your depth first search. And that will also give you a tree that spans the graph. So I'd like to explain that now on paper, because this is actually how you're going to do the problems. So, when we're talking about mazes, many years ago I was given this book on just a single maze in this book, in which you have pages and pages, in which you sort of have to work out what vertices are connected to what vertices and so on. Terribly complicated. I mean, I can't remember this, but it seems that I worked out the graph that's associated to that maze. But this is the sort of graph you might be interested in practice, and you want to search that graph. Obviously, the examples we're doing in this, that I'm showing you, are too simple. I mean, they're very, very simple. But in practice, one might want to sort of search the network of that detail. Okay, so let's go back to this simple maze graph. So this is the graph from the lecture notes that corresponds to the corridors in my grid maze. Okay, and the vertices have been numbered. So I want to do this depth first search. So let me just remind you what was written in the notes. So there are two methods for searching graphs. Two methods which we need to know about. For searching, for investigating, if you like, graphs. So the first method, which we're going to do first today, is called depth first search. It's going to go deep down. That's abbreviated DFS. And it works by recording the data in a stack. And then the other method, which we have actually seen before, is the breadth first search. And this works by using, it's sort of characterized by storing the data in a queue, in which you come on one end and go off the other end. Now, there was a good illustration of that, those that came to Cumberland Lodge, when Irina spoke about, at one point, about playing chess or playing Go. There was this sort of tree of possible moves from the start, and you might, if you're stupid, you might consider all possible moves. You start from a given position, and you look at all possible moves from that position. That would be a breadth first scenario, and then choosing each one of those moves, you look at all possible moves from that position. So by the time you've gone 2 or 3 moves, you've sort of run out of computing power. But that would be a breadth first search. But in practice, these algorithms would actually assess the position of each point and sort of discard what would be apparently stupid moves, and therefore, for a given position, you might only look at 2 or 3 subsequent positions. And the advantage of that is you can actually go much deeper down into the game, and maybe you can see what's going to happen after 10 moves, and that would be more of a depth first search. So think of it in those ways. Those are the sort of results of these 2 different searches, and we'll see that later on with the trees that they produce. But anyway, let me now use the method 1 on this graph. So let's search this using a stack, but I'm not going to write the table because that's in the notes. Let me see if I can sort of explain this more briefly in terms of writing on paper. So let's use the depth first search on this graph. See how we can do that. So the way I'm going to implement this, and there are different ways of doing this, is we're going to add, at each stage, we're at a given vertex, we're going to start with 7. So at each stage, we only add one vertex. Add one vertex, one adjacent, you always look at adjacent vertices. So we're only going to add at most one adjacent vertex at a time. And typically we take if they're labelled, if they're not labelled we can choose. If they're labelled we take, say, the lowest one or the lowest one in the alphabet if they have letters. Taking, for example, you can choose, of course, taking, for example, the lowest label first. So only one adjacent vertex at a time to the stack. So let's do that now. So it means we start with 7, because that's the starting point. And we look at the vertices which are adjacent to 7, because they have to be adjacent vertices. And there are 2 of them. There's a 3 and there's a 12. But because 3 is less than 12, I add on 3. After the 7, I put the 3 and I ignore the 12. Okay, so here the 12 is ignored because it's a higher number. And then at 3, you said at each step you're at a given vertex. And you can think of a sort of, as if it's Google Maps, you're at a given vertex, so that thing is sort of pulsating, and then you're looking at adjacent vertices. So 3 is going to scan all possible adjacent vertices. Think of it as a little robot that's sort of looking for adjacent vertices. And the adjacent vertices are 2 and 9. Well, we're going to choose 2 systematically, even though we can see as humans it's useless. But we choose 2 if we're going to do this systematically because it's a lower number than 9. So 2 goes on, and then we're at 2 and we look at adjacent vertices. But there's nothing new. We don't put 3 again on because we happen to know that 3's already been visited. So perhaps we have a separate list that tells us which vertices we've actually been to. So 3 has been visited. So we don't we don't put 3 again, we just remove the 2. We do what's called backtracking. So we're at 3 again. I mean, in practice, a computer might do this differently. The computer might actually pull all the vertices adjacent, but because it's a stack, you're only going to see one of them. So it wouldn't have actually done any harm to put, if we started with the biggest vertex first, we might have put a 12 here. That wouldn't have actually changed what's going on. So in practice, you might have repetitions in the stack, but the way I do it, you don't do that. So then we're at 3 again, so we put 9. I'm going a bit more quickly now. So we put 9 as the adjacent vertex. We're now positioned at 9. We look for adjacent vertices. I only want to put 1 at a time, so the one I put next is 1. And the one I put after that is 4. But 4's a dead end, so we have to backtrack to 1. Then I can put 6. Then I can keep going. I can put 5. I choose 5 over 10. But I have to backtrack because 5's a dead end. So I'm back at 6. 6 is now back. I've removed tray number 5, thrown it away, so I'm back to tray number 6. Then I can put 10. And if you like, I've finished if we decide that 10 is the finish, but I'm going to actually go on and do the whole graph. So after 10, I can go to 15. Have to curve down a bit here. And after 15, 15 is adjacent to 14 and 16. 14 goes first. Now, 14 is adjacent to 9, but 9's already been visited. So 14 does no longer see 9. You pretend it's been removed. You only consider vertices which have not already been visited. So 14 only sees 13 at this point. And 13 is a dead end, so we have to backtrack to 14. But 14, there's nothing else to visit, so we have to backtrack to 15, actually. So we've taken 2 trays off the stack. We're back at 15, and then we can put 16 on, and we've got to 16. But at this point, we realise that we haven't got all the vertices because we're missing this clump here on the left. So then we have to actually backtrack all the way. I'm not going to cross it all out, but we do have to take all these vertices off the stack and go all the way back to 7. Okay? So one way of sort of indicating this is that, let's just do it again. We're starting at 7, then we add 3, and then we go to 2. But how did we get 9? We got 9 because we sort of had to backtrack there. And then how did we get the 6? We got the 6 because we backtracked to 1. And how did we get the 10? Because we backtracked from 5. And then we went forward, 10 going to 15. And then we had to backtrack. So the 16 actually came from 15, like that. So this is sort of giving you a bit more information about, rather than doing this whole great table like in the notes, I can do it a bit, I can sort of summarise what went on like that. And then we have to backtrack all the way to 7 in order to see 12. So we remove all these vertices that are still there in the stack, and we can finally, if we remove them all, they're all sort of covered up, and we're back to 7, and then we can see 12. So we then put 12 here, and I can indicate that by saying that 12 gets scanned by vertex number 7. And there's a big sort of curve over going from 7 to 12, and then we're almost finished. 12 sees 8. We have to backtrack, and finally we get the last vertex, 11. And then if you like, you can then backtrack and get back to 7, but I've got all the vertices, so I'll stop there. That's the idea of a depth-first search. Okay? Again, if you're thinking of it as some sort of game, if this graph represents a game position, you may have sort of decided that going to 12 was a useless move, so that it's best to go to 3, and some of these moves are useless, so you get quite quickly to the end 10 by this method because you're not wasting time looking at all possible moves, you're going deeper into the thing. That's the idea. Now this gives rise to a tree. this search because we're actually getting to every vertex, and we can summarize how we've got to every vertex by means of a tree. So these searches, of course, I mean, first of all, let me ask you, is this graph a tree? No, why is it not a tree? Doesn't look like a tree, but that makes no difference. What's the definition of a tree? Why is this red graph not a tree? It has a cycle. It's almost a tree, but it has this cycle here. Okay? If I were to remove one edge, it would be a tree. Okay, so it's close to a tree, but it's not quite a tree. So the red graph has a cycle. What is it? A 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. Has a 7 cycle. So not a tree. But we can scan the graph with a tree, so corresponding to this search. So let me tell you how that goes. So I need this data here to try to explain. So we get the search, the depth first search gives rise to a tree, gives rise to what's called a spanning tree. Spanning means includes every vertex of the graph. So tree means a subgraph that is a tree, no cycles, but it includes every vertex. And we just have to sort of say how we got to each vertex from each other vertex. So we just have to record the adjacencies we used. So in particular, you see, one thing we didn't do was we didn't actually get to 14 from 9. We got to 14 from 15. So what's going to happen in this search, I think, in this tree, is we're not going to see this edge in the tree, in our search tree, because we never used that edge in our search tree, because we'd already gone through 9, so 14 could not see 9. So this edge was sort of not used. So let me draw the tree by hand then from the curvy line of data I have above. So we started with 7, and we have to cover every vertex. At the end of the day, I have to tell you how we got to 3. Well, we got straight from 7 to 3. Which side shall I put it? This side. But we also got from 7 to 12. Towards the end of the game, we also got from 12, obviously, to 8, and also to 11. But from the interesting part is what happened after 3. Well, obviously we got to 2, better put 2 there, and we got to 9. And from 9 we got to 1. Okay, it's important to realise that we didn't go first to 14. From 1 we got 4 and 6. You can still see that. And then from 6 we had 5 and 10. I think we remember more or less. And from 10, 5 was a dead end. The dead ends sort of, you can see easily, they're the leaves of the tree. From 10 we got to 15. And from 15 we got to 14 and 16. And from 14 we got to 13. So we've got all 16 vertices, and that is the so-called Dfs tree. There's a slightly more elegant picture of it in the notes, but you see the level, if we start from 7, you can think of that as the root, because you're starting there. If you want to get, you see it goes quite deep down, you've got 1, 2, 3, 4, 5, 6, 7, 8 levels to get down to 13. So the distance between 7 and 13 is 8 edges. It's gone quite a way down. And so how many edges are there in this tree? There's 16 vertices. How many edges? In a tree, 16 vertices, therefore? 15. It's always number of vertices minus 1. It's a tree. Okay, E, number of edges is always n minus 1. 15 edges, I hope. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Whereas the original graph would have had 16 edges. In fact, you see there's no 9 to 14, so 9 to 14 is missing. I don't think anything else is missing. So edge 9 to 14 from the original graph is missing. Is that clear? I did that. So you just, you know, when you carry out the search, although we're not using a queue this time, nonetheless we're using the notion of adjacency. Every vertex that is put on the stack because it's adjacent to the top tray on the stack. Okay, so every time you're using this adjacency, you're using the top vertex on the stack and you're putting another one on, you're using adjacency, and that means the edge goes into the tree. But because of the way you're doing things, you're never going to get a cycle. You never get a cycle because you never revisit the same vertex. So you're going to get a tree. Now let me do the same thing, but using the concept of breadth first search, and we're getting a different tree that way. So let me put to understand the method properly, it's a good idea to look at the notes and see that dirty great table again. Let me just put it up before we move on. So at the bottom of the page is sort of my abbreviated scheme, finishing at 11. With the braces giving the sort of jumps when you have to backtrack. But the table there is actually showing exactly what happened, and it's telling you for the stack it's telling you what the stack looks like at every stage of the game. Okay, so the stack is biggest when we've added vertex 13, and then 13 gets taken off, and then the stack gets smaller and smaller until we eventually add these vertices at the end. Okay, so that's and if you actually think of adding vertices to the stack, then you have to remove them to get when you backtrack, and so you remove all the vertices, all 16 vertices, particularly if you go back to the starting point. You'll see that all 16 vertices have been added at one point. Each of the 16 vertices has been added at some point and then taken off at some later point. If it's an easy dead end, it gets taken off immediately. But if it's something like 7, it persists for an awful long time before it gets removed. In fact, it gets removed right at the end. Actually, 3 was the better example. 3 meant we were turning left at the start. And that gave us most of the graph, but it left out this part, so we had to remove the 3 stayed on all the way from the top down to this point, but then the 3 got taken off in order to search the last bit of the graph. Okay, let's do the same thing now with a breadth first search.